Today's talk is going to be about graph transformations, or going from one graph to a graph that looks similar but located somewhere else or slightly different shape. To do that, we're going to be doing vertical shifts, horizontal shifts, okay, stretching it along the vertical axis or shrinking it along the vertical axis, stretching it and shrinking it along the horizontal axis, and then we have two other ones which are reflections over the x or the y-axis. Okay, first thing you want to notice is that all the vertical shifts, okay, the vertical shift and the vertical stretching and shrinking, we're doing something outside of the f of x. Okay, for the horizontal ones, we're doing something inside of the f of x. Okay, the reflections may look different, but when we reflect it over the x-axis, we're taking it from the top to the bottom, so we're actually changing the y, which is why where the minus sign is outside of the f of x. And vice versa for reflecting it over the y-axis. Okay, first off, okay, a vertical shift. What we're doing is, again, outside of the f of x. We're going to add or subtract a value. We'll call it c. In this case, c will always be positive. Okay, so we're going to either add a value, in which case we're shifting it upwards, or subtract the value and we're going to shift it downwards. Here's an example. Okay, the function is y equals x squared. That's the green line you see in the picture in the lower left right hand corner. Okay, when we add 4 to it, okay, the original function was x squared. We're adding 4 to it, so now it's going to be the red line. Okay, we've shifted the function upwards by 4 spaces. Okay, similarly, if we subtract 4, then we're going to shift it downwards by 4 spaces, okay, by 4 units. Sometimes it's helpful to look at it in a table format instead. So here's the snapshot of a table. I took 5 points. They were all nice integer numbers, so that's kind of why I took them. And if I do f of x, the first column here on the left-hand side is my x. The second column here would be my y, or my f of x for the original one. Okay, and then all I did is I added 4 or subtracted 4, and I regraphed them. Okay, actually I had the computer regraph them, but if I was to do it by hand, that would be what I would do. Okay, horizontally it's a similar concept, but now we're going to change the x inside of f of x. So to shift the graph to the right, I'm going to subtract the value from x, okay, x minus c. Okay, and to shift the graph to the left, I'm going to add a value to x. Okay, so let's see how that works in table and graph form. Okay, again, the function is y equals x squared, and I'm just using the green line as my original. Okay, if I wanted to shift it 2 squares to the right, I need to subtract 2 from the x, or x minus 2. Okay, and when I do x minus 2, the whole x minus 2 ends up replacing the x, or wherever x was, it's now going to say x minus 2. That's why the function for the blue line is now quantity x minus 2 squared. And the red line, which I'm shifting 2 to the left, I add 2, it's going to be quantity x plus 2 squared. Okay, and again, in table form, it's up here on the upper left-hand corner. Okay, if I start with minus 2 in the middle column, f of x plus 2, if I start with minus 2, f of x would just be 4, 2 squared, minus 2 squared. Okay, but when I add 2 to minus 2, I get 0. 0 squared is 0. And that's how this table started. Okay, I didn't do the ones on the other side. It really wasn't all that necessary. It gives you an idea of what it looks like, and since especially because my x squared is a kind of an even function or symmetric function, I could just draw the other side. Okay, and I did the same process with f of x minus 2. Okay, sometimes the table format is very helpful to help you understand like just exactly what's happening. That's especially true when we get to the horizontal and vertical shrink and stretches. Sometimes it's really hard to imagine what's going on, and so doing a few points on a table can help you straighten that out. Okay, so to change the shape of my graph horizontally by either stretching it or shrinking it, I can multiply the x-axis, multiply the x in f of x by a constant, again, a positive value c. Okay, to shrink or squeeze the x-axis, the constant c must be greater than 1. Okay, so in the case of the red line, okay, my original graph being the blue, now my red line, I kind of squeeze it in, okay, I took the x-axis and really just squeezed it by a constant everywhere. Okay, 2 becomes 4, okay, so in this case, 2, if x was 2, now x is 4. Okay, and so what I've basically done is I've taken all the values and squeezed them in, okay, by that constant 2. Okay, so to stretch the graph, or to get the green one, the constant c must be less than 1. Okay, and that way I stretch it out. C can't be 0 because then I end up with nothing. If c is 1, it's kind of pointless because I end up with my original function. And we're sticking with the values of c being positive. Okay, and so if c happens to be negative, then it's actually 2 transformations, because the second transformation would be a reflection over the x-axis or something like that, or x or y-axis. That would actually be over the y-axis. Okay, so, okay, again, an example here. Okay, so here I'm putting data in, and I think the table version makes more sense in the case of the horizontal and the stretching and the shrinking. Okay, it's kind of hard to imagine it otherwise. Okay, so here we are with f of 1/2 x. Okay, so 1/2 being my constant c. Okay, and in this case what I'm trying to do is I'm stretched out. So -2, okay, now becomes -1. -1 squared is 1. Okay, so I would plot that point on the graph, and it would be right here. Okay, on the graph, -2, 1. Okay, and then I would have 0, 0, so nothing's moved. Okay, and if I wanted to, I could get kind of like 1, 1/4, and then I would be able to, roughly draw my curve in there. Okay, and then it's a parabola, so I could just keep going, or I could look at the other points I've plotted. Okay, similarly for f of 2x. Okay, in this case, my constant is bigger than 1. Okay, so what I'm going to do is plug in 2 times -2. Well, -4 squared becomes 16. Okay, so it's way off my graph. I can't even see it. I didn't take enough points. Okay, but -1 becomes -2. -2 squared is 4. And so I would have this point, okay, at -1. I would have this point at 4, and 1 at +4. And again, I could just kind of sketch out this graph. Okay, so that's how we could use the data table to help us figure out, like, what is this graph going to look like? Am I stretching it? Am I shrinking it? Just exactly where are those data points? Okay, I don't think it's quite as easy as just shifting it either up, down, left, or right. Okay, same with when we go to the vertical shrink and stretch. Okay, again, we're going to multiply by a constant. This constant, because we're changing something along the vertical axis, okay, we're going to be changing the constant outside of f of x. We're going to just multiply the whole function by a constant. Okay, so in this case, what we're going to do is, if it's less than 1, if c is between 0 and 1, we're shrinking the y-axis. And if it's greater than 1, we're stretching the y-axis. Visually, it's kind of hard to tell the difference between this graph and the horizontal graph. Okay, there is a difference, but it's really subtle and it's really hard to tell. So it's not always easy. You really almost have to go to the table format here. Okay, to tell whether am I stretching the x, am I stretching the y, if all I see are 2 different graphs. Okay, so again, in table format, these are the values we get. We could plot them and end up with the different graphs. Okay, blue being my original one, red, constant c is greater, so I just kind of stretching the y-axis and kind of like, imagine being kind of rubber band, just pulling everything upwards. And the green one being what happens when I kind of like smush it down a little. I'm shrinking the y-axis. Okay, and again, my constant there is less than 1. The last ones are reflections, okay? Reflections across the x-axis. I talked about that minus sign, okay? And basically all I'm doing is I'm taking all the values and changing the sign. Okay, so if my original graph was the blue graph, it's now the red graph. Or vice versa, okay? If my original graph was the red one, it's now the blue one, okay? That's what a reflection is. You can't tell which one's the original and which one's the copy, just about, okay? Reflections across the y-axis. Now I'm changing the x itself, the minus x. Okay, and so this is a graph of x cubed. If I reflected x squared across the y-axis, I don't see anything change actually. So this is x cubed. Okay, again, you can't tell which one's the original one and which one was the reflected one. Okay. When there are multiple operations, the order of transformations follows PEMDAS, okay? Or same order of operations. So if I had this function g of x is equal to 2 times f of 1, it's really, really complicated. Okay, there's 4 transformations going on here. I could even get more transformations by putting the reflections in as well. Treat the reflection as its own operation, okay? It's a multiplication. You're basically multiplying by a minus 1. So it goes along in the same area as any of the horizontal shifts, or as any of the stretch functions. So if I look at this one, the first thing is like, okay, well, I have the parentheses associated with 1/2 x plus 3. So I have to do the thing in parentheses first. Okay, and so my first thing, well, I also have the multiplication and then addition in the parentheses. So what I have to do first then is the multiplication of the 1/2 x, or horizontal stretch. Then I add the plus 3, which is a horizontal shift, 3 spaces to the left. Then I do the 2, because that's a multiplication, okay? And so that's a vertical stretch. And then I have the minus 2, which is a vertical shift, 2 spaces downwards. Okay, and you would actually graph each one separately because it's hard to keep track of them all and it's impossible to do it in your head. Okay, if you did it as a table, it's not so bad. But this is what happens when you're trying, as you're going through all the operations. My original function is the blue function, f of x. Okay, this one here. Okay, that's my original function. Okay, let's get rid of that red line so it doesn't confuse us. Okay, the first thing we need to do, like I said, we have to do the f of 1/2 x. Okay, so I'm basically stretching it out along, squishing it down along the y-axis. Okay, so it gets squished down and I end up with the red curve. Okay, and I didn't do the table just because I didn't really have space on this thing, but there's in the background did the table just so I could have points to plot. Step 2, like I said, I need to shift it 3 spaces to the left because I added 3, and so I have the light green line. Okay, step 3. Now I'm stretching it along the horizontal, squishing it along the x-axis by multiplying by 2, and I end up with the purple curve in there. Okay, and then step 4, I have to subtract 2, and I end up with my orange line, which is simply by shifting it 2 squares downward. Okay, so that's the purple shifted downwards by 2. So we kind of have to go through all of these one step at a time. Okay, you could do it as a table. I don't, I definitely recommend that to act kind of as a double check to see if it makes sense to you. Okay, it's up to you kind of what points to choose. I think it's fairly clear most times, like any of the points like minimums and maximums are always good. So, this point here where I started, that's a good point to choose. And then I would kind of just look at integer values to one side, things that look like they're going to be really good integers. Like this point here would be a good one, okay, 2, 4, or, if you can't see it in this thing, but, 1, 1 in this graph, okay. On the red graph, like if this is where I started, this point would be a good point to choose, okay. Any of the integer ones are good because integer math is a lot easier than having to deal with decimals, Okay, so that's transformations. If you have any questions, please write them down and we'll try and answer them in class next time I see you. Thank you. Bye-bye.